In section 2.3. All right, folks, let's stop talking, please. Biconditionals and definition. So before we even talk about about our topic, what is this? When we put this bi prefix in front of a word, what does that tell us? What does bi mean? Two. So we're going to be talking about two conditionals. Biconditional means two conditionals. So what we're going to do is define a biconditional, and then the biconditional or biconditional statement, and then we're going to do a little. We're going to figure out how we make one, and then we'll do some practice with it. So a biconditional. And we could say biconditional statement. We usually just shorten it by saying biconditional. So a biconditional is a combination of a true conditional statement and its true converse. So just like we had with the opener. We had our true conditional statement. If today is Tuesday, then tomorrow is Wednesday. And then we've had a true converse. If tomorrow is Wednesday, then today is Tuesday. So that's a combination of a true conditional and its true converse. What we do to make a biconditional, we join them with if and only if. So what we could say for our opener is we could say today is Tuesday if and only if tomorrow is Wednesday, and that would be a biconditional. And in symbols, we write a double arrow, or sometimes you'll see it as arrow like this. And we read this P if and only if Q. So just like we said before, for our opener we could say today is Tuesday if and only if tomorrow is Wednesday. We could also turn it around and say tomorrow is Wednesday if and only if today is Tuesday. We could say it in both directions, and that's why we have the arrow pointing in both directions. So we can turn it around either way. And this is a combination of if P then Q, and I'm just gonna write it in symbols, and if Q then P. Oh, and I forgot to mention for the quiz tomorrow, we will at the top of one of the pages of the quiz we'll have the symbols like this. If P then Q, we would say conditional statement, and it would have this. For the converse, we would switch it around and say converse and have the Q arrow P, and we'd have the same for the inverse and the contrapositive. So the little symbols for each of those. That'll be on the top of one of the pages of the quiz to help you out tomorrow. So when I wrote this, it made me think of that. So a biconditional is a combination of if P then Q and if Q then P. That's why we have the arrow pointing both directions. And what we use biconditionals for is to make definitions. So that's how we use them in math. So what I want to do, I have a little activity where we make a definition. We figure out what some thing that we don't know anything about. We come up with a definition for it by coming up with a biconditional. All right, so questions about what a biconditional statement is. And remember that a biconditional statement has two conditional statements, a conditional statement and its converse. So it's two pieces. We can put the two pieces into one, and we can also take the two pieces apart into two conditional statements. All right, so let me grab these pictures. I know they get, when we magnify them, they get a little bit blurry, so bear with me on this one. But I like this activity, and I'm going to make this a little bigger. So this is a picture of, these things are called floppers. And we want to figure out what a flopper is. We want to come up with a definition for floppers. And these things are not floppers. This is going to help us come up with our definition. Those are not. Those are not floppers. And then here are some that once we talk about these a little bit, we're going to decide whether or not they are floppers. Hello. You can come on in. All right. Oops, I thought I paused that. All right, so let's look at this first one. Let me make this one a little bigger. And what we have here, I know it's a little blurry. This is an A, a B, a C, a D, and an E. All right, so looking at this first one, what do floppers have? What makes something a flopper? So it's some kind of shape, right? Yes. It has three dots. Okay. Is there anything special about where the dots are? One inside. Two outside. Can we be more specific? What else do we know about floppers? What's that? They have tails, right? And the dots are connected by tails. What's that? You don't have to. You don't have to draw. This is more just for us to think about how these things work. So can we consolidate this a little bit? How could we say this rather than in three different statements? How could we say it in just something a little shorter? Anybody? So let's combine all this together. So floppers have a dot inside and two dots with tails outside. Is that just to combine everything together? So why is this one not a flopper? What's wrong with this one? Doesn't have three dots? How about this one? This one has four dots. What's wrong with this one? Too many dots, and it has two inside. Why is this one not a flopper? It only has two. It doesn't have a dot inside. All right. So let's look at these. Which one of these five are going to be floppers? E is a flopper. E and D, dot inside and two with tails outside. So those two are floppers. So let's see if we can write a conditional statement and a converse for a flopper. So I'm going to say if it is a flopper, then what are we going to say? If it is a flopper, then what does it have?
It will have one dot on the inside and on the outside.
So let's just say it that way. Then it has one dot on the inside, two dots outside. So that's one way to describe a flopper. Let's write the converse. Let's write the converse of this. So if we're going to write the converse, what do we do for a converse? Flip it, turn it around. So if, what's going to be our new hypothesis here? If it has one dot inside and two outside, then it is a flopper. Is the converse true? Is this converse true? If it has one dot inside and two outside, then it is a flopper? Yeah? So we have our conditional statement, true. Converse, true. So we can combine them into a biconditional statement. I'm going to say it is a flopper if and only if it has one dot inside and two outside. So this is our biconditional statement that combines these two conditional statements, this conditional statement and its converse, into one biconditional statement. It is a flopper if and only if it has one dot inside and two outside. And this could be our definition of a flopper. We could use this as a definition of a flopper. It is a flopper if and only if it has one dot inside and two outside. So this is how we go about making a definition in math, is we use these biconditional statements. And if we drew a Venn diagram for both parts, so I could make a diagram for the first conditional statement. So my little category is going to be flopper. And my big category is going to be one, I'm going to say outside, two inside. And then for the other one, the converse that is true, I would say these just switch around. So one in, two out, and flopper.
The first one, would it be one outside or one inside?
Oh, sorry, did I write it backwards?
Yeah.
One in, two out. So this would be our Venn diagrams that talk about both, that have to do with both of these conditional statements. And then we can turn them into a biconditional statement. So the biconditional statement combines two conditional statements, the true conditional and its true converse. So we can always combine two conditional statements into a biconditional, or we can undo a biconditional into two conditional statements. All right, questions on our little activity there. All right, let's do. Let's do a little bit of practice making another biconditional. So here's my example. Here's my conditional statement. If two angles, and we're talking about their measures here. If two angles add to 90 degrees, then they are complementary. All right, is this true?
Yes.
If two angles add to 90 degrees, that's what we said complementary meant, is they're added to 90 degrees. So this is true. The truth value of this is true. Let's form the converse. So what do we do for our converse? How do we form a converse? Turn them around, change the order. So if two angles are complementary, then they add to 90 degrees. Is that true? If two angles are complementary, then they add up to, their measures add up to 90 degrees? Yeah? All right, so let's write the biconditional. Two angles are complementary and what am I going to say for a biconditional? If and only if they add to 90 degrees. And that would be a definition for complementary angles. Two angles are complementary if and only if they add to 90 degrees. We could also write it in the other order. We could turn around the other order. It doesn't matter which one we do first. So we could say if two angles, or we could say two angles add to 90 degrees if and only if they are complementary. So I could put the other part first. Sometimes it's harder to do that. This one is not too bad. So two angles add to 90 degrees if and only if they are complementary. That would be our biconditional. A different way of writing the biconditional. We can do it in either way. So remember, a biconditional, we take a conditional statement, its converse, and we put them together into one statement with if and only if. All right, questions there? All right, really quickly, definitions. This is how we're going to connect our biconditionals with definitions. Definitions need to have three things in math. So we want terms that we know. So when we came up with our definition of floppers, we talked about dots and lines. So we used terms that we knew to define our flopper. So we need terms that we know. We need them to be precise. So we didn't say each flopper has a little thingy hanging from either side. We said it had dots. We said it had points, something like that. So we need to be precise. And the third thing we need for a definition is it needs to be what we call reversible. And reversible means that we can write it as a true biconditional. So when we say is our definition reversible, it means can we write it as a true biconditional? And true, I mean the truth value has to be true. All right, so let's look at a couple of examples. Let's talk about some definitions and decide if we have a good definition. An equilateral triangle has three congruent sides. So we want to decide, is this reversible? Is this a reversible statement? Can we write this as a true biconditional. So if we wanted to write this as a biconditional, how would we write it? I'll start you out. A triangle is equilateral. So what are we going to say next?
The triangle is equilateral of three sides.
So we want to write it as a biconditional. We want to see if it's reversible, so we're going to write it as a biconditional. If and only if what? It has three congruent sides. I could also have written a triangle has three congruent sides if and only if it is equilateral. We could write it either way. Is this true? A triangle is equilateral if it has three. Doesn't equilateral mean three of the same sides? Yeah. And can we say it the other way? If it has three of the same sides, then it is equilateral. Is that true? Yes. So yes, this is reversible. So this is yes, reversible. And I should say, our question here was this: is this reversible? I want to know if that's reversible. Yes, it's reversible. This would be a good definition. A good definition is reversible. Terms that we know. We know triangle, equilateral, we might have to think about a little bit. We know what congruent means. So this is reversible, so it would be a good definition. So that would be a good definition of an equilateral triangle. So based on what we've talked about the last couple of days, how would you guess we would show a biconditional statement, or show that a definition is not a good definition? Both conditionals aren't true, and what did we say? What did we find to show that a conditional wasn't true? Counterexample. We find a counterexample. To show that we don't have a good definition, we find a counterexample. Counterexamples are very, very powerful. So I want to write some definitions, what I think are good definitions, and I want you guys to find counterexamples. So here's my definition of a dog. Dogs are animals with four paws. And that's my definition of a dog. Is that a good definition? No? Why not? What's that? Can't reverse it? If an animal is a dog, if and only if it has four paws? That doesn't work? No? What would be our counterexample? Cats. There's one counterexample. Cats, bears. We were talking in the last class whether cows had paws. No, you don't think they have paws? They have hooves. Could we consider those hooves paws? Maybe. Maybe. All right. So this is a cats is our counterexample. So this is a bad definition. All right. Here's my other definition. Let's focus, guys. Squares have four sides. That's a bad definition. We can't say a shape is a square if and only if. Let's stop talking, guys. A square is a shape is a square if and only if it has four sides. A rectangle has four sides, right? So that would be our counterexample. Rectangle has four sides and it's not a square. So this would be a bad definition. All right, next one. My next definition. Tuesday is the day before Wednesday. So this is kind of like our opener. Tuesday is the day before Wednesday. Could I say it is Tuesday if and only if it is the day before Wednesday?
Yes.
Would that be true?
Yes.
Could I say it is Wednesday if and only if it's the day before Tuesday?
No.
Did I say that right?
No.
I didn't say that right? If today is
Like it is Tuesday, if and only if the day before.
the day before is Tuesday, yeah. It is Wednesday if and only if the day before is Tuesday. Is that true? Yeah? So we can reverse this? It's reversible? Precise enough? So this is a good definition. This would be a good definition of Tuesday. As long as we knew what Wednesday meant, right? Last one. An acute angle is small. That's my definition of an acute angle. No?
That's like an opinion.
That's an
Opinion.
what do we mean by small, right? Is 89?
It could be 89 degrees and some conditions are
Right. So what's the problem with this definition?
Opinion.
it's biased.
And it's wrong. It's wrong in terms of how what we said we needed for a definition.
Consider something to be small.
What we said it needed to use terms that we know.
Needs to be precise.
Needs to be precise. Small is not precise enough. So this is an opinion. We need precision. So this is not precise, so this wouldn't be a good definition. All right. Questions on reversible? Questions on definition? Okay. Our homework, page 101. We're finally in the 100s.